can you think about a picture of this? What would be the picture? So if I would like to visualize it, what would be that kind of picture actually? I know it's quite difficult to embed in, Euclidean space. Okay. But roughly, it's going to be bunch of points, discrete points. So like a point is here, and a point is here, and a point is here. So you have bunch of points, okay? Lots of points. Okay. But all these points has a weird property that all of these points are at a distance exactly one from each other. Okay? So, it's such kind of a maybe picture, it's not a good picture, where you take any 2 points. Okay, so this picture at the moment, gives an illusion that maybe the distance between this point and this point is 2. It's not the case actually. In discrete, you should have all points are arranged in such a way, okay, that you take any 2 points, the distance should be always 1 actually. So like I take these 2 points, the distance should be 1, and these 2 points, the distance should be 1, and so on and so forth. Okay, so it's roughly a picture, okay, this kind of a space, but
सेंटर से 1 होगा, अगर
हाँ?
रेडियस 1 रखे तो सेंटर से 1 होगा, पर सर्कल के जो सर्कमफ्रेंस वाले पॉइंट्स होंगे ना, उनका 1 नहीं है.
So in other words, as I said that it's quite difficult to embed in Euclidean dimension. We can embed it. We can embed it, but then the metric need to be infinite dimensional actually, to really stay in Euclidean space. Okay. Anyway, but roughly is going to be this kind of thing. Okay, you have discrete set of points put in such a way, weird way. Okay. You take any 2 points and the distance is always. Well, that's not a good picture. Don't
You
think
can
that.
just draw 4 points here, not more than that.
But there are not only 4 points actually. So there are lots of points here. Okay, so my point is that it's going to be roughly look like that. So it's like things are discrete, stay in such a way, okay, at different places. That you can take any 2 points and their distance is 1 actually.
Triangle, equivalent triangle, sir.
Okay, making sense? Okay. So let's think about, in this very weird space, the meaning of open balls and closed balls. This should be very funny. What do you think? Wouldn't that be funny? So one thing is difficult to visualize. So now we want to say, so that's what the beauty is. You even can't visualize it, but still you can find and you can do analysis. Okay. Okay, so we have discrete metric, and in discrete metric, think about your effects. So open ball. So the open ball is collection of those points of x for which the distance between y comma x is less than r, where r is a positive number. So what do you say?
1 is less than r.
What do you say? So one hint is that think about the relationship between r and 1. Okay, so r.
If r is greater than 1, then there could be other points, but if r is less than 1, then it would contain only x.
Is it making sense? So just think about it. So if r is smaller than 1, so in other words, if you want to, so you have these discrete points, and on this point I want to draw a ball of radius less than 1. Then apparently it's going to contain one thing. But if I would like to draw a ball which is equal to 1 or greater than 1, what's going to happen? So since all of the distance are at, all of the point at a distance 1 from each other, so it's going to contain everything actually. Is it making sense?
All y is not equals to x.
It's going to contain everything. Think about it. So if r is smaller than 1, then Br of x is set of those points, okay, for which Byx is smaller than, say for example, r, okay, r, why should I wrote it? I should have written it directly. So if r is smaller than 1, so if r is smaller than 1, okay, then which is the point y that you can put here and in such a way that this inequality holds? So if I put something different from y, something different from x, so this number would be what?
1.
So 1 is less than r and r is smaller than 1.
Yes.
So can it be true that 1 is smaller than something which is smaller than 1? Okay. So the conclusion would be, yes, you can't have anything different than x actually. Because if you put x here, then the distance between x and x is 0, and 0 is less than r, which is fine, so inequality is satisfied. So if I put anything else than x, then this inequality would not be true. Why? Because y can't be, 1 can't be smaller than r, which is smaller than 1. Okay? So in that case, this is going to be singleton x. Okay? So the singletons is going to be the ball. So in other words, in that picture, if you want to draw a radius smaller than 1, is going to contain only that point actually. Okay? But, just think about it. But if you want to draw a ball on a point which is of radius 1 or bigger than 1, then it should contain everything. Why? Because all of the points are at distance 1 from each other. So all those are going to be encapsulated between.
सर लेकिन वहाँ पर ट्रबल ये होगा कि हम उसे पिक्चराइज कैसे करेंगे?
Huh?
सर वहाँ पर ट्रबल ये होगा कि उसे हम पिक्चराइज कैसे करेंगे?
No, obviously you can't picture it in dimension.
Sir, not everything except itself. X खुद नहीं आएगा ना वहाँ पर.
Why not?
अगर x आ गया तो वो 0 हो जाएगा. And r is greater than 1.
No, but like r is greater than 0, so it's fine.
R is greater than 1.
We only need, mathematically what we are demanding, we are demanding which are those y's which satisfy this inequality.
I'm talking about the later case.
Oh, yes, yes. I mean, it's fine. For example, if I take y to be x, then distance between x and x is 0. And r bigger than 0 is true.
Sure.
So x is always true actually.
Always.
Okay?
Yes, I got it.
So if r is bigger than or equal to 1, then no matter what y put here, or I put here, for example, which is different from x, this difference is going to be 1, okay, and which is true actually, which is true, okay. But there is going to be one trouble. We can't have equality here. We need to put equality here actually. Okay, even if we take r equal to 1, it still is a troublemaking thing. Why? Because if r is 1, then the distance between y and x, which are different from each other, is going to be 1. And the inequality that is going to be 1 is smaller than 1. But can 1 be smaller than 1? It can't be smaller than 1. So hence, 1 is also not a good radius actually. Okay? Unless you are taking a close ball. Okay, then it's fine. Okay? Anyway, so if r is bigger than 1, then every single point of this space is going to be in Br of x. Why? Because you take any point from here, the distance between that any point and x can be at most 1, while the radius is strictly bigger than 1. So in other words, this inequality is going to be satisfied for the all points actually. Okay? So it's very easy to think in the terms of Euclidean metric. But when you change metric, things will get weird actually. Okay? Things will get weird.
Sir, why we have taken R is greater than or equal to 0?
Which one?
In that one, R is greater than 0.
Then it's going to be inconclusive actually.
So then,
I mean, R is greater than or equal to 0 is included here. So when you are saying that R is less than or equal to 1, so at least it could be something which is bigger than 0. So we are saying that when you are saying this, basically I mean this actually.
if we have taken x, then if there will be distance from x to x, then that will be 0. And 0 will be less than R. So it will be, radius will be of 0. So
Okay.
we have taken there that we should.
Okay, let's take R to be 0.
Yeah.
Okay, and dx x to be and dx dy x would be what? So you have two possibilities. Either y and x could be equal or not. So if they are not equal, then the inequality would be 1 is smaller than 0, which is obviously not true. And if y and x are equal, then the inequality would be 0 is less than 0, which is also not true actually.
You also can't take R is equal to 0, I think by definition of balls.
Yes.
No, I'm talking about why we have taken R is greater than or equal to 0.
इस वजह से नहीं. The reason is this, that R equal to 0 is a troublemaking thing actually. Okay? R equal to 0 is troublemaking thing. And if you are, for example, including 0 into it, then you are saying that you are not moving away from that point actually. So if you will, for example, take some radius, then you will have some points in your ball. I mean, if you are taking R equal to 0, that means that you are at that point itself. So it's not going to be something trivial. You are not defining a new thing actually. The new thing would only make sense if you take R to be bigger than 0.
लेकिन 0 लेंगे तो उसमें तो ओपन बॉल के लिए होगा dxy less than 0.
और ये
Less than 0 तो कोई पॉइंट नहीं, मतलब वो itself भी नहीं होगा.
Oh, yes.
क्योंकि वो
So there is going to be lots of troubles. Okay. R equal to 0. But it's fine to ask such questions. Okay. How about closed ball? And so it's set of those points which are less than or equal to R. So you can have again two cases. If R is less than or equal to 1 or less than 1, okay? So if R is less than 1, then VR of x is going to be singleton. It's going to be the only that point. And if R is greater than or equal to 1, then VR of x is going to be full space.
Closed bar equal space.
Full space. ठीक है? Is it making sense? So let's move ahead a bit. Not take, say, for example, x equal to r, but let's take, say, for example, x equal to r2. Okay? So x equal to r2. So x equal to r2 is going to be what? What would be the metric on this, basically this r2? So you can have many matrices, okay? But it's a finite dimensional space, and we're gonna learn afterwards, not in this course, in function analysis, that if you take any finite dimensional metric space, then somehow any two metrics are equivalent to each other. You can't have, so actually you have only one matrix, so the rest are the versions of it. So you can just derive one from other. So some matrix looks very different from each other, but you can prove that okay, they are all equivalent to the Euclidean matrix.
Even this discrete also.
Even discrete also. Again, so not discrete. Discrete is going to be a bit. Discrete is going to be a bit different.
Execable, visual.
So in other words, you can show that actually. You have this result. Some versions of this are maybe not have exact statement, but I do have a statement about norms actually. That any two norms are equivalent on finite dimensional normed space, but but we know that there is a relationship between norm and matrix. So
yes, sir,
somehow you can
yes.
force this result in matrix spaces as well. Okay, so we can take what you call the Euclidean metric. So dxy equal to what? So it's going to be, so if x is comprised of say x1, x2, and y is y1, y2, then okay, so we can take, so in that case it's going to be x1 minus y1 square plus x2 minus y2 square, something like that. So x1, x2 and y1, y2. This is going to be the notion of distance between them. Okay? So what is your guess? What would be open ball in this metric? It's going to be the set of those points for which dyx is less than r. What is your guess if I would like to see on Euclidean plane actually? So how it would look like? So it's going to look like a disk actually. So you're going to say that okay, Euclidean space, if you pick a point and choose a radius, okay, and you take all those points which are within this radius, okay, which are within this radius, then set of all these points is an open ball actually. Is an open ball. So it's going to be kind of an open disk. So when I'm saying something open, that means that there is no boundary in it. Okay, we're going to make it dotted out. Okay? And similarly, if you take a closed ball, you're going to see a closed disk. In other words, a disk with boundary included and shaded out. So it's going to be the key. Okay? Okay. ठीक है, चलो move ahead.
जी सर.
Alright, I mean if you see from Rudin's terminology, Rudin calls these open balls as neighborhoods. Okay, so from Rudin terminology, neighborhood and open ball are
R and every space. In R
in
and
any space.
any space.
Okay. So let me write some definitions and let's do some more examples. So this terminology is very important. Okay, you need to make sense of it in a proper sense, because then this language is going to be used again and again and again and again. Okay, you need to be very careful and very open with this. notion. Okay, so let me define a neighborhood, with a notion of, with reference to a notion of Rudin, using Rudin. Okay, but you're going to see that it's almost the same thing. Alright, neighborhood, NBD. This is my shortcut for that.
सर यहाँ बाय आर्बिट्री तो उठा रहे हैं
Uh-huh.
बाय उठा रहे आर्बिट्री कोई भी
Uh-huh.
ये क्यों उठा रहे हैं आर्बिट्री कैसे उठाए नहीं कैसे
No, obviously,
X comma Y.
no, obviously, you can't pick points outside X. So this belongs to X. Obviously. No, but like it's an arbitrary point of X. So it's like those points of X which satisfy this inequality. Okay. So do you think that we can call, say, these open balls as a neighborhood? What is your intuition about neighborhood? Neighborhood is what? Neighborhood is what? Pados. So you have your house. Okay? Okay? You have your house, and we say that 40 homes around you in your neighborhood. So you have a set of points, set of houses that you can treat as the neighborhood of your house actually. So you are defining a radius, okay? 40 houses, right? 40 houses around your house is basically your neighborhood. So it's really the intuition actually. And actually you see that the definition that we are writing, that we written basically previously is precisely the same thing. We're saying same thing in a same manner. So let XD be a metric space, and a neighborhood of a point P in X is a set, as you have set of houses around your house, okay, is a set NR of P. So it's like neighborhood, of around your point, okay, with radius R, okay, such that, okay, is a set of all points Q, such that the distance between Q and P is smaller than R, which is exactly the definition of open ball that you have just defined. Okay, so with the Rudin terminology, Rudin uses the notion of neighborhood for open balls. I'm not getting into examples of this because we have already done it. For closed balls, obviously you will have. Okay. Okay, what would be the Rudin's notion? Okay, Rudin is not interested in that at the moment. I guess in closed balls. So he is interested in closed sets at the moment. Later on he defines basically the things which are equivalent to what you have in closed ball. Okay, closed sets. Okay. So I would like to define next thing, which is going to be a kind of a interpretation of this thing. What do you think that what should be the meaning of a set E being near to a point? Yeah, not near to a point, because if near to a point, then you can say it's a neighborhood. But I'm saying that approaching to a point.
Set approaching to a point.
To a point. Yes. Yes, kind of. No, it's a set. Well, we are saying that, what do you think that what should be the meaning and how should we define a set being approaching to a point? So it's like so it's like a set of points is getting near and near and near. So in neighborhood is this property. So it's like here you say that okay, you have set of points which are in the neighbor of this point x, but we can't see that the points are getting near and near and near. So you can be away, you can be near to basically point x, but it doesn't have this property that a set is kind of being approaching to a point P. So if this is the case, then what do you think that how should be the picture actually? You can just think about the picture and then basically we can basically kind of drive a definition out of it. Huh?
एक फिक्स पॉइंट लेंगे
We'll do the fixed point.
फिर ई के सारे पॉइंट्स का डिस्टेंस जीरोस इसके साथ जीरोस को अप्रोच करेगा
Epsilon.
किसी
यहाँ हम सिंपल बात करेंगे वो
Alright. So that's a description, but I would like to see the picture. So okay, you have real line, this line, and you have a point here. Okay, and I want that a set is getting near and near and near to, or an element of sets are getting near and near and near to a point. So what do you think? What should happen actually?
T will be minimum point of view.
Central to x.
it's just like the
What's the limit point?
Minimum point.
Minimum point. Okay.
it's just like the convergence of a sequence to a point
What's a convergence? Do we know the convergence?
As we start,
से यहाँ पे बहुत सारे पॉइंट बनाने
So let's take some points. Shall I go this way?
उसका डिस्टेंस है
Shall I go this way?
राइट साइड
Just like, okay, so I have.
से क्लस्टर बना दें क्लस्टर
डिस्टेंस विल बी गेटिंग reducing
minimum distance.
So it's like, the set of points in this E are getting closer and closer and closer to this point in other words. So in other words, at this point you are having a kind of a cluster. A cluster of points E. Take it? And just think about it now. Now, if I take this point B and take a small neighborhood of this point, okay? Do this neighborhood is going to contain the points of E?
not
No, I'm not saying that do this contains some points of E.
Yes, sir.
Yes, it does.
The answer is going to be, it does actually contain some points of E.
yes
What if I make it even more smaller?
it again
It should contain.
So
Some points.
even if I make it smaller and smaller and smaller, because this is getting nearer and nearer and nearer, are you getting the point? No matter how you make this neighborhood smaller and smaller and smaller, it is still going to meet with this set here. Okay. So we gonna say that if I have a point, okay, and a set in such a way that you take any neighborhood of this point and it meets with the set E, then you're going to say that somehow E is approaching towards this point. In other words, for this set we have a limit point.
yes sir
Sir, whatever epsilon or radius you will give, I will give you points in it.
We can easily try such a kind of a thing. So here's the intuition that somehow the points of a set are getting nearer and nearer and clustering at a point. So I would like to define this in a rigorous term, in a mathematical term. Okay. Okay. Definition. Give me the definition. What do you think that? So here a set has a relationship with a point. Now we are saying that a point has a relationship with a set actually. Somehow the set is getting there. So what do you think that we're going to say that a point P is a limit point. The limit point of
set
A. Okay. If what happens?
There
exists a
for all balls, we
In
can.
other words, no matter how small ball you use,
For all balls.
for any neighborhood of of this point, you know, there is going to be at least one point which is in E, different than P, you know, which basically, you know, which this neighbor is going to contain. So in other words, we are going to say that, you know, every neighborhood of this point is going to meet with E, is going to have something in common with E, obviously other than P.